this condition in the first step we check. So it's obvious that it's 1 on A, 0 on B. Condition in the first step we got that it's harmonic, and we also had this theorem, if you remember the first lecture, that in this context at least, this had a unique solution. So we exhibited the solution, so there is only one H that satisfies those three conditions. What did we do that first lecture? More or less, okay. We also check the extensions, but we don't need to put it now. And last time, last time before Andrei, Dimos, remember that P, we discussed the invariant measure. So the invariant, the probability on the set of vertices, if you remember, it means that P of X was the sum of Y of P of Y, P of YX, for every X. So the sum is only the Y. So that we interpret it as if we sum the measuring Y times the probability to go from Y to X, so all of the probability that arise in point X, if we start with the P of Y already, it is exactly P of X for every X. So like at this point, here there is P of X, it goes here, the probability. Here there is P of Y, it goes here, probability P of YX. Here there is some other mass, it goes here, there is some other probability. What you get here is exactly, P here is exactly the sum of how much it can, that form, how much it enters from every vertex, from every arc of that definition. This was the same as saying that if we start with probability P, the probability that our process is in some set A is exactly P of A for every, and most importantly for every time n. So this is obviously true at time 0. If I start with the low P, the probability that x0 is in A is exactly P of A, is the definition of I start with probability P. But invariant means that it's the same for every n. And we check this, but the equivalent from, it's equivalent from here. This means that the sum over S of P of X, LF of X, is 0 for every X. Okay? Just write here f over y minus f over x is one goes here. Okay, we check its immediate calculation. So this means that, we check that if we start with some measure at time 0, this measure evolve, will have a new measure at time 1, like the law of the process at time 1, the law of the process at time 2, and so on. Invariant means that they always stay the same. Actually, we also checked the other time in the other time we checked that there exists a unique pi invariant. So an invariant measure is given by this formula. But in the case of a finite graph, irreducible, so what you're assuming today, we prove that it exists and it's unique. Is it clear the meaning of this? The meaning of invariant? Sure? Yes. Okay. Invariant, but what was what we spent most of the time last time was to give an explicit representation of the invariant measure that was P of X, if you remember, was the sum over all the spanning, I don't remember if I call them gamma, or they call the spanning trees, was the theta maybe theta, was the sum over all the spanning trees of the graph B rooted at X of the product of the edge of the spanning tree of the probability of the edge. So for instance, if this was B and this is X, this was spanning tree rooted at x. You remember these pictures we drew last time? That's where we spent most of the time actually. And so P of x is the product of this and P of this guy is just the product of this and this and this and this and the product of all the arrows. And to note that invariant measure of x, we have to sum over all the possible way of drawing a spanning tree over the graph rooted at x, so we are finished up this amount. And this gave us a explicit representation of the invariant measure through this combinatorial representation. This is more or less of what we did last time. So, with this in mind, where do we want to go now? What do we want to what tools do we want to use and for what motivation? So we have this graph. We can think, I'm thinking, for instance, about what's called Monte Carlo Markov chains. So we have a typically very large graph. People in computer science, they like lattices. So this is like a large portion of Z2, okay? But maybe you can think a large portion of ZD. But finite, cut, because people want to put it on a computer, for instance, so it will always be finite. And we do some, we want to sample. Do you understand? We want to sample. We want to sample, like we want to generate, we want to pick up randomly points on this lattice, finite. According to some measure, okay? And there's a well-known problem that even if you know the measure, when D is large, it's very time-consuming to kind of generate this measure and simulate it on your computer. And a fast way to do it is not to actually generate the measure, kind of explicitly and exactly, but to run a Markov chain on this graph, whose invariant measure, this one, is the one you want to sample. Okay, so instead of kind of calculating exactly this measure, you just run a Markov process, Markov chain in this case, that has that one as invariant measure. And then what you do, you start, it's not important where you start, you run your simulation, you follow your Markov chain for a long time, then you stop. Where it stops is the point that you sampled according to that invariant measure. Why? Because there is a unique invariant measure, and I don't remember if we discussed much, but it's like, if I start in any s, in this irreducible case, the probability that, say, xt is equal to y, for any y, this will converge, no matter who is x, to p of y, where p of y is the unique invariant measure. Okay? So, of course, if we start already with p, that's not a limit, it's an equality, but if we just take t to infinity. Okay? This is informal, it's just some motivation of what we are doing. Okay? And now, that's good, but good question now, for how long do I have to, I want to simulate, say, my measure with some precision, maybe, or within some error, for how long should I run the process? Because usually this stuff, they run it on very powerful computers, what's called supercomputers, so it's really very expensive. Could simulate in half the time, you save kind of a lot of computing power. So what we're thinking here is we would like to know kind of how this convergence happens, and in some suitable sense, okay, these different people can be interested in the convergence of this invariant measure in different senses, but we will focus just on one sense, okay? And it's like maybe so if you call mu t the lower time t, no matter where you started, and you call it pi, the invariant measure, the distance in some sense, Wasserstein if you know, but even total variation in this case, this will be roughly, say, bounded by the distance between the measure at time 0, so the probability at time 0, so if I start in x, this is just the delta x or any other measure actually, and pi times to some exponential of minus p over some internal time scale of this process. Let's call it capital T. Okay, this capital T encodes, depends of course on who was the process, right? So, it's not exactly this, but say it's something like the supremum over all the x and y of the expected value where I start in x of the time it takes to hit y. Why? It's quite clear that this is an internal time scale for the process. If I want to simulate my invariant measure, if I want that my process is close to the invariant measure, it needed that the process explored in this time t more or less the whole graph, right? It's clear that if I don't give enough time for this Markov process to enough steps to visit on average the whole graph, there is no possibility that we didn't discuss any distance of probabilities, but no matter what distance you put it, if this time is too short, it's clear that the lower time t, if you start in any given point, which is not already pi, will not be close to pi if you don't give to the process the time to explore everywhere, because it will not see some part of the graph, so how can it live? The invariant measure depends on the whole graph, how can it simulate the invariant measure if you don't give it the time to do it, right? So what the idea is just one motivation for what we're doing, but the idea is I want to sample a measure, so I want to extract points randomly from this graph according to some given distribution pi. I simulate a Markov process with invariant distribution pi for a long enough time. But how long, I cannot know during the simulation. It's not like the simulation tells me I arrive to the invariant measure. I have to know it analytically. I have to know it a priori. Okay, I have to know how long should I do it in advance. Okay. So what I would like to do in the next lecture is first to give a representation for this kind of objects, expected time, when you start, say, with some given explicit measure of it in time of some set, okay, and then to use it to get a sharp asymptotic of this object for some classes of graphs, okay, in some specific cases, some specific asymptotic, okay, so that at least in theory you can have, you know and you want an error of this size, you know analytically how long you should run your simulation. That's the motivation. Okay, that's the motivation for what we are doing next. So, the idea is that, so more in general, what is a problem. Let's take A and B, which are subsets of B, and are disjoint. Okay. What we will do is find analytic representation of the expected time. When I start with a suitable measure on A, this we will choose. This will be a probability measure that we will choose for our own convenience. It's not arbitrary, but of course if A is just one point, there is only one probability measure on that point, which is the delta concentrated at that point. So this will be a probability measure on A. Okay, we will define it later. This we have to choose in a sort of smart way to have the calculation work. But if A is just one point, like in the example before, it's obviously just expected value starting in X. Or the first time I hit B. Okay? So we want to write B equal to, and we want to have variational formulas for this object here. I want to write it in a way that in many different asymptotics it's kind of easy to estimate in a sharp way. So for this, usually you use variational formulas. You write this object kind of as a supremum and as an infimum. So if you want to know that this is bigger than something, okay, supremum on stack, you just put a test inside and it will tell you that it's bigger than that. The infimum, the opposite inequality, right? So that's what we're going to do. We're going to use some basic potential theory to get this representation. Okay. And what I do not want to do is to assume reversibility. So let's give a simple definition. Remember we have the pxy. Okay. These were our data. Pxy. That's all what we know. Okay? And from these we know that there is an invariant measure pi. Let's define P star of xy as simply P of y, P of yx divided by P of x, right? You remember that this was positive at every point, just made reducibility, so this is well posed, right? It's just P of x, P star, pi of x, P star xy is P of y, P of yx. And notice that the sum over y of P star of xy is also equal to 1, because pi was reversible, so when I sum over y here, I get exactly pi of x, and the denominator is pi of x, so this is 1. And of course, P star is positive. So these are also transition probabilities on our graph. Okay? We started with a graph, we just made a new transition probability, a priori different from the one before. These are called adjoint or reverse transition probabilities. Okay? So in particular, if P star, we will avoid this hypothesis. We don't want to make this hypothesis. P star is equal to P. The process is called, so pi actually, the measure is called reversible. But we will not assume reversibility. Things are a bit simpler in this case, but we will not assume. So as we did before, I will always put a star on the object, kind of the analogous object that we define for P, but if we use P star in place of P. So we will have first another remark. You can check it immediately from the definition. Sum over x of P of x, P star of xy is equal to P of y. Right? Because if I put P of x here, this goes away. I sum over x, the sum of this is 1, so I get P of y. So the measure pi is invariant both for P, I mean, without any assumption of reversibility. Yeah? The measure pi is invariant both for P and for P star. Right? This is exactly the condition of invariance. So P star is a kind of, if you start with the initial measure pi, exactly the invariant measure, P star is the transition rate for the process going backward in time. But in any case, it's a new transition curve. Okay. So I mean, I have my P, I can do it this simple way, the P star, once I know the invariant measure, we know that it's positive, so no problem about numerator and denominator, so it's positive everywhere. And it's invariant also for these new P stars, so we will call, like, I don't know, P star x, the probability associated to the transition rate P star, small P star, okay. From the small p we got to the big Px. From the mod P star, we will call it capital P star. I don't know, we had, for instance, this function HAB, the probability of touching A before B. We will have similarly an H star AB and so on. Every object, when there is a star, means the one associated with these rates, with these transition probabilities, not with this. If there is no star, it's with this. Okay. And we can also call this just notation Ts of xy, the symmetric part. So it will be just P of xy plus P star of xy divided by 2. Okay. And similarly then, okay, we had L, so here also, here we have the L, like we will make a left, we will have L star F. So this, for instance, is just, the sum over y of p x y star f of y minus f of x. It's just not, I mean, like I don't start, I don't say every time. I consider the p made from p star. The star is. Okay, then this is just notation, so. Let's start in some sense. Definition, the Dirichlet form P of S and G is bilinear, but not symmetric, just bilinear. Form, say, formally is on L2 of pi. We have a finite set, so L2 of pi for us are just functions from B to R. Okay. So who is this? I mean, it's a very specific one. And is defined E of fg is just the sum over all the x in B of minus P of x LF of x G of x. So if you want, is just the sum over all the x and y of P of x pi of x, p of x y, f of y minus f of x, g of x. So you see, in reality, it's just the scalar product in L2 of pi of LF with G, right? If you like, this is just P, so minus P of G LF. If P of something is integration with respect to that. So in this case, just sums. So just notice very quickly these are very good jokes, but just I'm unable to use them here. They are very fast, but I try to. Do you read what I remarked? Third, if you want, E of fg is also equal to pi minus pi of f L star G. So in other words, L star is nothing but the adjoint in L2 of L. Right? So FG, G LF, or F L star G. Okay? It's not very difficult to check it. It's just, you see, indeed. What does it mean? We should check that the sum over all the x and y of P of x, P of xy, f of y minus f of x, g of x is equal to the sum over all the x and y of P of x, so I do this now, P star of x and y, g of y minus g of x f of x.
Excuse me, what is F or L? What is L?
For L, you remember you maybe one chance we already read. L is an operator on function LF of x is the sum over y of p of xy f of y minus f of x. And, well, L star is the same thing, but here is a star. Well, you can check it. Quite easily, probably, just because, just by the definitions, the term g of x f of x, g of x f of x, g of x, pi p star, once you sum over x, they are the same, and the other two terms, f of y, g of x, g of y, f of x, they are just the same in the sum, just you have to exchange x and y. So it's not like the terms are all the same, but the sums are just the same. You can, it's just an exercise in, change the variable x with the variable y, and you just rewrite it just the same. Actually, if you want, you call L star the adjoint, to of L, and then you check that P star are just defined as we wrote before. So in particular, if I do P of f, the E of f is equal to minus this, and is also equal to minus this, because it's f is the same everywhere. That means the g equal f. Every time we g equal f, that's correct. And something is not convincing me. Did I write it right? L F L star G. So this is also equal to 1/2 the sum of rho x and y of p of x, p of xy, f of y minus f of x squared. So in particular it's positive. If you want, we can check this fact quickly. So E of f is minus the sum P of x, pi of x, P of xy, f of y minus f of x, f of x. I can write it as well as minus. So the sum is on the x and on the y. Let's do something. It's exactly I have the right to put here s. Let's put s. It's exactly the same sum. The symmetric part, you remember? So here I want to put pi of y, pi of yx, f of x minus f of y, f of y. I wrote exactly the same thing. I just changed with the name of x to y and the name of y to x. right? So the sum of x, y is exactly the same sum. But now, this is phi of x, p of x and y, phi a star. So this is equal to this, and is also equal, so if A is equal to B, that's also equal to 1/2 A plus B. So if this we call it A, and this we call it B, since they're equal, they're also equal to 1/2 A plus B. Okay? And now if you do the algebra, you just, you see, this f of x minus y is exactly this with the change to sign, you will get exactly this one. So it's a linear form, which is not symmetric, but it's still positive on the diagonal. I don't think we will use this, but it's good to know. Let's check if I want to say something more on this. No? Okay. And and now we give a crucial definition in potential theory, and it's called the capacity. So yet another definition. So A and B, subset of B, and this joint. H of x is the probability of an instructing x and the probability is less than B, and the capacity of A and B between A and B is the capacity between A and B is just the Dirichlet form of H. This is minus the sum of x of phi of x, h of x, and h of x. And notice that if you remember, so this is the sum over all the x in B. But h was 0 on B, and LH was 0 on the complementary of A union B. So the only x where this guy is non-zero is A. That's minus the sum over all the x in A of phi of x, h of x, and LH of x is, if you remember, will be just the sum over all the y of p of xy, h of y minus h of x. So, okay, we already knew that this was positive, but I want to say something more. You see, we can restrict the sum on x in A, and here we have p of xy, h of y minus h of x. But for x in A, h of x is 1, and h is a probability. So h of y minus h of x, no matter where is y, is h of y minus 1, that the probability is negative. There is a minus here, so not just this sum is positive, but each term of the sum is positive. Okay? So here we say the sum is positive, using that. But for this special h, each term of the sum is positive. Because, okay, 0 out of h, and equal or bigger than 0 inside of A. Thanks to this, we can define another object. This is called, given A and B as before, A and B as before, this is sometimes called a harmonic measure. So in potential theory, there are two different things called harmonic measure. So this is sometimes also called equilibrium measure. But also equilibrium measure is used in different contexts. We call it mu, but it depends on A and B. This is a probability measure on B, which is actually concentrated on A. Okay? Mu of X is just 1 over the capacity between A and B times minus P of X, H of X, LH of X. So this is 0 if X is not in A, that's what we just said, and bigger or equal to 0 if X is not. Okay, it's this. What we just said is that each term in the sum was positive. So this mu of X is positive because this divided positive constant. The sum is 1, right? Because the sum was exactly the capacity. So mu is indeed a probability. Okay. Okay. This is a somehow classical object, in particular the capacity, developed by 19th and early 20th century mathematics in the reversible case, but the applications to non-reversible are a bit more recent. You will see the difference, hopefully, in a few, maybe today or next time. And okay, just a remark. The capacity between A and B is equal to the capacity between B and A. Okay, and is equal also to the capacity star between A and B. So star is the one defined with H star in place of H and L star in place of L. Okay, let's check this simple fact. Actually, so we have H, A, B, okay, well, we just call it H, because the probability is in point X, when I start in X, that's so A is more than for B, so it's just 1 minus H, B, A. If I change A and B, T tau B less than tau A is just 1 minus. So the complementary, then, so, if we want to do the capacity between B and A, this will be just the Dirichlet form of HBA, HBA. So it's minus pi of 1 minus HAB, L of 1 minus HAB. But now L, when it acts on constants, is 0. And it was a linear operator that was 0 on constant, because it was P of xy, f of y minus f of x, if x is constant is just 0. So it's minus pi of, so this means this notation is clear, yes? Pi of a function was the sum over x of pi of x, the function at x. Now the function is this whole guy here. So L on 1 is 0, so we get 1 times minus LH AB minus pi of H AB LH AB. Okay, but if you remember, invariant measure was such that phi applied to L of whatever function was 0. You remember, invariant, you recall the beginning today, we saw it last time, was P of x1, f of y minus f of x was 0 for every x. That was the equivalent definition of invariant measure. This was 0 for every x. So in particular, it's 0 if I put here h. So this guy here is 0. And so we are left with exactly minus pi h LH, the capacity within BM. And just to prove that is equal to cap star, so let's continue here. Okay, so we have the cap AB. We have written just here was minus the sum over all the x in A of pi of x, h of x, LH of x. So it was enough to consider x in A. But now you see, this is equal to minus the sum over all the x in B of pi of x, f of x, LH of x for every f such that f restricted to A is 1 and f restricted to B is 0. Because, I do the reasoning I did 1 second ago in the inverse way. I put in place of, since I'm restricted, H, remember, was 1 on A, 0 on B, and the harmonic in the rest. But this sum is just on A, so this h of x in general is just 1. Okay? So on A, I can replace h of x with f of x, and here I still have the sum on A. But then f is 0 on B, so I can put sum of A union B. LH is harmonic on the complementary of this set, so this is 0, so I can put just f of x. So in particular, is equal to minus the sum for all the x in B of phi of x, h star of h, LH x. Because h star was the probability of touching one set before the other, but still with this condition, still satisfied this condition. Was for the adjoint process, for the adjoint generator, but who cares, it satisfies these two conditions. It's one of these f. H star, I take as f, in this formula, I take f, h star. It's my right, H star satisfies these two conditions. Okay, and now I use the fact that, so this is what, if this is minus A of H star LH, so it's also equal to minus pi of H L star H star, because L star was the adjoint of L, so I can just change, if I put it on the other function, one function L or another function, I just change the function on which L acts, and I put a star. And and then it's the same thing as before, just apply the two star. This is, if you want, okay, is minus the sum over all the x of pi of x, h of x, L star H star of x, but it's the same as restricting this sum just on A, because this is 0 on B and this is a L star harmonic out of A union B. So I'm just doing the same kind of reasoning over and over. So these will be the same no matter what function that takes the value 1 on A and 0 on B in the place of this H. So I can just put H star. And so this will be the capacity star of A and B by definition. Because it's the Dirichlet form with respect to L star of H star. So it's the capacity star. It's elementary, but just okay, the A for the Dirichlet form, I just sum on A. If I sum on A, I can replace that with anything with these two properties and do the Dirichlet form. Then I put once H star. Once I did this, I do the same reasoning, but for star. So, okay, I just get this. It's really elementary computation. And as you can understand, it's kind of, we are not really, you are just using the Markov structure, like generators and Bayesian methods, not really our graph and so on. We discussed very quickly Markov processes the first time. Okay. So why it's called capacity? Because if you think that the process is reversible, so that P of S, if it's an if, we are not assuming. So you see, instead of, if you have this symmetry, instead of thinking that the graph is directed, so there are arrows, you can think that the graph is not directed, just links between points without an arrow. So you think really that you have an electric circuit, I don't know, something like this, and you call this CXY. And this is like, 1 over the resistance between the points x and y. And then if you take two sets, I'm sure in the high school you made, or maybe even before, you made this sort of pictures, no? Maybe. And then, I don't know, if I take A as this set, I take, so in this special case, B as this set, I put potential 1 here, potential 0 here. The capacity between A and B is the power dissipated, so the energy of a time dissipated by this circuit. Okay, so that's... so these definitions really come from electrical networks. These names, okay? Because, there is quite intimate relationship between linear electronics and reversible operators. So self-adjoint. It's exactly the exactly equivalent. Okay. Very good. So let's make a lemma for our let's leave and f function from B to R and define U of x as the expected value when we start in x of the sum between 0 and tau B minus 1 of f of xy. So what's this stuff? So this is, here is the set B, okay? This is a random, he is very drunk man starting in point X. Okay, he's here. He moves randomly, so it is here. This is a pub, this is a pub, this is a pub, this is a pub, this is a pub. This is his wife. When she meets him completely drunk, she kills him, or maybe just closes him in his room. Okay, so the guy, if he goes in the pub Y, he drinks f of y shots of vodka. Okay. So this is, so B is the set where he is stopped by his wife. Okay. So this is just the expected value of how much he will drink before he stops. Right? I sum until the moment, the last moment before he meets the wife. So tau B is it depends on the one path. Tau B is the function of the infinite path, right? It could be as big as, we don't know, it depends on the path. He would just do some loop here around here a very long time. But then, just we sum, so we come up to this random time. It's a random sum, it's sort of discrete time for an integral, right? It says this, right? And how much it drinks at time I until this final time tau B where he stops. Okay. So, and U of X is the expected time of this thing when you start in X. So we look at it as a function of the starting point. Then, so what the lemma is that then U satisfies that U of X is 0 effective in B, while LU is equal to minus F on B minus B. So here, so in B, of course, the function is 0. If you start already at home, you will not drink anything, right? But if you start here, this value is not harmonic, but LU is equal to minus F. Okay, the proof is exactly as we proved that H was harmonic. Just we just condition on one step, but it's not complex. So conditioning on the, so if X is not in B, okay, if X is in B, this is obvious. If X is in B, this is obvious. If X is not in B, then U of X is the sum of a y of P of xy, the expected value when you start in X of the sum f of xi, given that x1 is equal to y. So this is equal to the sum. So we condition on the first step. Like if the first step is in y with probability pxy, so if I condition here on the first step, I have to multiply by the probability that the x1 is y, and this is this one, and I have to sum over all the possible outcomes, right? And then this is the sum of y and b of p of x and y. But now let's check what it is. So the term I equals 0 is just f of x. I start in x. Okay, the first term is in y, but I start in x, so I equals 0 is just f of x. So here I get f of x plus, and now here I have the sum from y to tau b minus, okay, let's try it. The sum when I start in x of the sum from 1 to tau b minus 1 of f of x I given x1 is equal to 1. But now, I don't care anymore here that I started in x, because I have Markov process. If x1 is equal to y, if I know where I am time 1, right, what's inside here only depends on what happens after time 1. So the poor young guy, once he reaches the point, say y, he doesn't care anymore that he started in x. From this point, he will start to follow the new arrows with some probability, right? So this is just equal. So now we should be a bit careful. Sum over y of p of xy, because what I said is not f of x plus. So here I can put, we should be careful. Just at the time when I start in y of the same thing of f, from 0, because now, so the first term here in the sum I start from y, right? The first term in the sum is y, of f of xi, and the solve, and that's exactly now u of y. I say you must be careful, because I didn't write here tau b minus 1. Because we should never forget that tau b is the function of the path x. Okay? So it looks like, wait, here there are tau b minus 2 terms in this sum. And if I want here u of y, there are tau b minus 1 terms in this sum. How can they be equal? There I summed tau b minus 2 things, here I sum tau b minus 1 things. No, they are equal. Because there is tau b of x, right? X. Here I made a change of time, I shift time by 1. So this is tau b of x I plus 1. So the tau b for one-sided scale, my new tau b is exactly 1 unit less than the previous tau b. So that's actually true, this formula. And that's why I get exactly u of y. Okay? And so that provided that x was not in b. Because if x was in b, this sum was already empty. Well, this may not be empty, because I forget that the first time 0 was in B, maybe the first step is out of B, so this is, and then the equality is false, right? So, so it's for x not in B, so this is in B, no. Okay. Okay, so what we got is u of x, this sums to 1, right? So I get exactly f of x, plus the sum of the y of p of xy, u of y, which is the same thing as LU equal to minus f. Okay, I put the u here and minus f here. So it's a very standard argument of probability. You condition on the first thing, you did it probably in the first time you see probability, all these exercises, the first coin flips, but there is only one delicate point to mention, that is this one. Okay. So let's remember what we discussed. We discussed, okay, the Dirichlet forms and capacity. There are all these things of the capacity. The harmonic measure, it was just a definition, and this lemma. And now we put these things together. Let's call it theorem. Is still. What I just want to say is quite simple. We just make sums, the things cancel out their own equalities, right? So far, now kind of estimates. But just let me tell you that we are not really using here, as usual, that we are on a finite graph. You could do this in a complete functional analytic framework. okay? If you have ever seen a bit of operator's theory, being on a finite graph just helps us to say that every function is in the domain of the operator. So I don't have to care every time that kind of, I can apply L to some operator, but otherwise we could just write it down all formally in this way, it would work exactly the same. Okay? If I would know that kind of my functions are, have you ever heard about this domain of operators? Like you are, for instance, on a Banach space, you have unbounded operators and things like that. Okay, here all our operators are always bounded because our space is finite. That's the real simplification. All the definition of informalities, they go through any other sufficiently regular matrix process. So theorem, so let A and B as before, so means just non-empty disjoint. F from B to R. H star, remember, is the probability when we start in X star that tau A is less than tau B, and pi the invariant measure. Let us given these things, then the expected value when I start in X, when I start, and we also have mu AB, the harmonic measure. Then the expected value when you start in X of when you start with mu, sorry. So I start randomly now. Okay. If A is a singleton, it's just 1 point, mu was the probability measure on A, so must be the delta in X. But in general, I just start with the probability measure on A, the one that we defined before. You remember? Minus pi of X, H of X, L, H of X. So if the poor guy, he starts randomly, and I sum how much he brings, right? This is equal, it's just an equality, 1 over the capacity between A and B of the sum over, so this in the notation that we use is pi of H star F, which now means 1 over the capacity between A and B, the sum over X of pi of X, H star of X, F of X. So in particular, the expected time when I start with mu of tau B, so that's exactly, in particular means I take F constant equal 1, is just 1 over the capacity between A and B of the sum of P of H star, pi of H star. Okay, the expected time. So that, if you remember, was our original motivation for today's lecture. I said, okay, I have to, for this to work, I have to choose these carefully. So I cannot start with whatever measure on A. But if I have these, I calculate these, I get this sort of explicit expression. You see, this, what is on the left, depends a bit on the wall part, right? Is the expected value of some sort of complicated random variable. What's on the right is 1 over the capacity, is this constant that is kind of the non-trivial part of this expression in some sense. But then here there is just the invariant measure, we have an explicit representation for it, and H star, it solves an equation. 1 on A, 0 on B, LH on harmonic outside. So for typical cases we have in mind, where we have this graph, so things of interest, things that are sort of, for instance, hard to simulate, or things that model metastability in physics, are the cases where there are traps on this graph. I don't remember the Russian for this. Like the process finishes in a trap. In a trap? That one. Yeah, exactly. And so in effect it just means that in some limit it will spend a lot of time around this point. Okay? So it will spend a lot of time, but finally he will also finish in this new trap. Okay? And then do again and again. So if we have an environment, so H star, like the probability, if I start here, if I start close to here to finish, so the invariant measure will be like concentrated almost entirely here, for instance, or here. So this is very simple to guess, because for instance, if the invariant measure is concentrated around here, H, the probability of this is A, this is B. Okay? H, or H star, will be roughly 1 here. So this is, it's kind of, you know, if you start in a trap and you want to know the time it takes to hit another trap, this guy is roughly 1. If the trap was a good one that would attract most of the invariant measure. So the bad part is just, you want to know just estimate sharply just the catastrophe. Okay? Like, you know, methods that you have seen maybe Ising models or dynamics for Ising models where, you know, this dynamic of 0s and 1 or -1 and 1. All -1 is a trap, all +1 is a trap, what it takes to go from one to the other. Very delicate and very difficult questions to know the asymptotic depending on the graph. Okay, let's prove this theorem. The proof is fast. So we want to prove this. Okay. H of mu of the sum from 0 to B minus 1 of xi. This is the sum of rho dx of mu of x. And if you remember time and expectation at the same time. This is what in the lemma we have called U of x. This is, if you remember, is just starting randomly with probability mu means starting in mu of x, starting in x, sorry, with probability mu of x. It's just the definition of the convex deltas. So this is a tau. Okay, so this is mu of x. So let's remember who was now mu of x. This is sum over all this b of minus phi of x, h of x, LH of x, u of x. But as usual, this sum is if you remember, was on V, but in reality it was just on A. This sum. Right? This is 0 on V, and this is 0 on the complementary derivative on V. So on A, h of x is 1. So this is 1. And then, so I can just write, sorry, no, what I said is not correct. So I just write it on V, sorry, what I said is not really correct. I want to give the sum of V, but still, now this is 0 on the complementary of A union B, and this is 0 on B. So if I put here 1, I can keep the sum over V. Should I say it again? So this sum is the sum over A union B union V minus, so this sum is joint, A union B. Okay? I have this guy. Now, here, this is 0. Here, okay, this is 0, I don't care, but this is also 0. And here, this is 1. So on all the terms where this is non-zero, where this is non-zero, this is always 1. So I can just put 1 here and keep the sum over the whole V. Okay, here it was H of X, but it's 1 if him is different from me. So this is just minus pi of U LH. Oh, I made a crucial mistake. So nu is what we defined, but with L star. Aha. So let's cheat. Let's call it here. So let's keep nu as we lead, but let's call this nu star. The guy with the star. Okay? So in the theorem, this we take the harmonic measure for the star process. Sorry. So here there are stars everywhere. Stars. Star. And here is correct. Okay? So here we get L star, H star. Sorry, I don't start with the harmonic measure, I start with the harmonic measure star. Just usually I think I would call this the harmonic measure and the other one the star, but okay, star is an evolution, as you can easily check. In any case, it's just the name of this measure. It's not important to put or not the star. So, but now this is exactly minus pi, so H star LU. You remember I can change L and L star, changing the function on which it acts. LU was minus F. But this was minus F. That was the lemma. The lemma we proved before this theorem say that if U of X is this guy, LU was equal to minus F on B. So wherever H star is non-zero, LU is minus F. Wherever this is non-zero, so in this integral, in this sum, LU is minus F. So this is, as we stated, divided by capacity. So in all these definitions, so nu of X is this guy, nu star of X, divided by capacity. Sorry, I forgot this constant. So it's this divided by the capacity. So it's this guy divided by the capacity. So it's pi of H star LF divided by the capacity. So we have this nice formula with this that we know explicitly. Okay, there is another thing where finite state helps, and this explicit expression of the harmonic measure. This we know explicitly. This is kind of easy to guess in the application I have in mind, and we need to know how to calculate, estimate this constant. You give me two sets, A and B. I want to know kind of the conductivity between them, okay, the capacity between them. And this is good. I want just to make one example of it. So now we have new problem. New problem. previous problem was give a representation for this guy in a way that kind of hopefully is good to give an estimate, to give estimates in some limit, in something. New problem, write capacity between A and B as infimum of something and as supremum of something. In this way, if I want to prove that the capacity is bigger than what I expect, I just test, okay, this something here with some object on which I take the infimum, and this will tell me the capacity is smaller. Then I test with something here in the soup, and this will tell me, since the capacity is the supremum, whatever I put inside here, the capacity will be bigger. If in some limit, in some asymptotic, this graph becomes the infinite, or other, I don't know, the rays do something, the probability transition do something, and so on, maybe I will get a sharp limit for the capacity. Okay, that's it. And so, it will be more complicated for us, but example, and this reversible case. Reversible case. Reversible case. If P of X, P of X1 equals to phi of Y, P of Y of X, basically a non-leaf, then the capacity between A and B is the infimum over all the function f from B to R, such that f on A is 1 and f of B on B is 0. So the same condition as HF, that HF of the Dirichlet formula. So what we are just stating is that, you know, so in this case, it's simpler. It's simpler. We will need to define things like, I mean, it's quite elementary, but it's like to make flows on this graph, use the Stokes theorems, a bit of discrete version of these things. It's not hard, but here functions are kind of, for the reversible case, it's simpler. It's just this formula. And then, what we get, wow, so let's prove this example. Proof. We want to prove that this infimum is achieved at H, right? This, by definition, was E of HH. That H was the probability of touching A before B. That H of X is starting next, probability of touching before B. We want to prove that this infimum is actually attained at F equal H. But okay, this is now, we are just minimizing the quadratic form with the restriction, right? Which is actually fine. So what you want is the basic example of any complex integration problem. So if G from B to R is such that f of X, G of X is equal to 0 for each in A and B, okay? Then F I wrote it actually I started with F. So proof F minimizes E of Ff out of all the functions here, if and only if, for all G from V to R such that G of X is 0 and A and B, E of F plus G, F plus G is bigger or equal than E of Fx. right? Because if f is 1 on A and 0 on B, f plus g has the same property. But now, due to this condition, this is a symmetric quadratic form. This is a symmetric bilinear form. Right? Because this was, I mean, E of fg, you remember this was phi of f Lg, but if L is equal to L star, I can take it here, so it's just symmetric. If you remember, this was the case L equal to L star, so E of fg is equal to EGF in this case. So now this is equal to EFF plus EGG plus twice E of fg. So is this big, when is this bigger than E of ff? For every g, so if this goes away with this is quadratic, so if there is a g for which this is non-zero, multiplied by epsilon, you can make it this is smaller, and this is you can choose the sign, right? Like when you make minimizations for derivatives. Right? So this is true. So this if and only if E of fg is equal to 0 for all g with this property. F was 1 on A, 0 on B. So this means if and only if the sum over all the x with the minus phi of x LF of x g of x is equal to 0 for all the f with this property, for all the g that are equal to 0 on H union B. Okay, but then for each x which is out of A union B, I can take g equal 1 on that x and 0 elsewhere. So the sum is 0 for all such g, even only if LF is 0. This is strictly positive. This I can take as a positive on a single point and 0 elsewhere. On each point in this sum, this away from A union B, this must be 0. So this is if and only if LF of x is equal to 0 for all x in B minus A union B. So these F minimizes if and only if this is true for all g, if and only if this is true for all g, this is the same thing as this for all g, and this is the same thing as LF of x equal to 0 for all x in B. So, but we have a unique F actually, with such property that is 1 on A, 0 on B, and harmonic on A union B. This F exists, and this F equal to A. Right? This was the theorem we proved in the first lecture. We fixed the values onto sets. There is a unique harmonic extension away from these two sets. So, okay, so the minimizer exists a minimizer, and this H, and so okay. In the reversible. So, for instance, in the reversible case, this problem is solved. Now, you want to prove that the capacity is smaller than something. Well, in some asymptotic, I can imagine how things work. So maybe I cannot write exactly with H, but I can maybe give a right asymptotic. I put the F, and I prove that the capacity is smaller than the amount that I calculate in this way. Okay. So actually, maybe as a reference. For reference, there is a review Alexandre Gaudier is a paper on archive 2009. don't remember, the title is Condenser Physics and Markov Processes or something like this. But this is reversible. So all the theory here is the reversible case. Okay. Of course, it just is not done. I think he works on a countable graph. But so we are just kind of forgetting these technicalities of this sum are finite, that not all functions are in the domain of the generator, but we are approaching instead non-reversible case. Okay, the reason is pretty simple. With the motivation we had in mind, is the motivation I told you of convergence to application to sample measures on any graph. Okay. The reason is very simple, is that out of all Markov processes that you can run with a given invariant measure, the reversible is the worst, is the one that converges the slowest. So it's really the one you don't want to use if you want to sample with this measure, with this method of measure. Okay. But say for kind of historically, it's by far the most well-known case is the reversible case. Okay, let's make this.